So I'm going to give a basic talk about assembly in terms of reverse engineering. So it's not going to be a talk about how you code in assembly, because that would take way too long. So first of all, this is me. My name's Sven. You can find me, or you can email me there, read about me there, Twitter me there, or see me on Freenode on IRC, and then you can find all the GitHub and stuff from there. So I'm going to go over the basic x86 architecture, kind of like what you're going to be needing to know. Calling conventions. Could I just ask, who's like programming apart from you? Who else does like programming or has done programming? Good, you have. Yeah. Okay, so it's a bit of basic, kind of assumes very little knowledge. So I'm going to go over some of the basic ops. There's actually only 7 you really need to know to get started, surprisingly, but there are a lot more, but you can sort of pick those up as you go. We're going to go over how to identify some common constructs, loops, switch statements, and the like, because they do, you know, they're quite helpful to sort of be able to recognize as you're going through the assembly code. And there's going to be some cats. There will. And if you have any questions at any point, just, you know, ask, or if anything's confusing you, or if you want me to slow down or whatever, just let me know. So why do we reverse engineer? Well, sometimes we don't know how stuff works, and we want it to know how stuff works in order to be able to plug our own things in or make it work with the things we already have. And we can't because we don't know anything about it. So we look into it, reverse engineer to get interoperability with other software, other hardware even, other communication protocols and such. We just want to know how it works. Curious as we are, we like to delve into systems and figure out exactly what they're doing and how they're doing it. Keygen cracks. I'm sure we've all had our fair shares of keygens and cracks. So you reverse engineer the serial generation protocol or algorithm to get your keygens, or the copy protection, or the 30-day timeouts to generate your cracks. Exploit development. So any sort of binary exploits can be found, probably easier found if you're targeting open source software. You're looking through the basic code, you can find all your vulnerable operations like string copies or allocations and deallocations or whatever, but sometimes you don't have that code. So you've got to find some sort of entry point, reverse engineer it and see if you can find any possibility of exploiting the application. And then also proprietary file formats. A lot of software uses file formats that aren't documented publicly, but we do want open source tools to be able to read those file formats. So we can actually look at these files and reverse engineer exactly how they're being read and what they contain. So I'm going to make a few assumptions about what you guys, all folks, know. You want to understand data types and sizes, bits, bytes, words, D words, Q words, and whatever. You understand hexadecimal notation and endianness, familiar, so that's in big and large and small endian. Everything's going to be in Intel syntax, so I'm not going to go over AT&T syntax. These are the kind of 2 flavors of x86 assembly. I like Intel. It's a bit odd because of the way the operands are ordered, but AT&T syntax is a bit noisy. But it's good to know both ultimately, but Intel's quite common. And you've programmed something before. I've seen a program, source code, not obviously the compiled software at the end. Okay, so I'm going to go over the first thing. One of the most important things about software is, or the way programs run, is the stack. Now the stack is an area of memory that the OS gives to your program, and it sort of grows and shrinks as the program runs. It's a last in, first out data structure, so anything that goes in goes on top, and anything that goes out comes off the top. So nothing, you can't take anything out from anywhere in between. It grows from upper memory addresses to lower memory addresses, and this is often quite confusing because a lot of diagrams show the stack as a stack growing like this, like a stack would, but that's your low memory and that's your high memory. So sometimes they draw it upside down, so you just kind of have to get your head around that. And then there's going to be a big mention about the stack pointer, which we'll go over in the registers later on. And it's basically used for just keeping track of function calls. It's used for passing arguments to other functions and to allocate local variables to each function. and every function that runs will have its own stack frame, i.e. a portion of the stack is allocated or freed up or assigned to that. Then there's the heap, which is essentially like the stack, but it's used for dynamic memory allocation, and that grows from low memory addresses up to the high memory towards the stack. The other sections here is BSS, which is uninitialized static variables, so something like char star string without being initialized. This data section is the initialized static variables, so the same as if you have char star string equals whatever, and then that's your actual program code in memory. And then moving on, so we're going to cover the registers now. So these registers on the CPU, which are basically behave like small chunks of memory, and they're really fast. So there's 4 general purpose registers, 6 segment registers, 5 index registers, 5 index and pointer registers. And you'll probably see the general purpose and index registers used more than the segment registers in sort of early on. So the general purpose registers are EAX, which is often used for return values, EBX, which is the base register for memory access, so you'll often have a value in there which points to a place in memory, and then you'll be working from that point with offsets. ECX is often used as a loop counter, and EDX as a data register for string operations. That being said, though, you can use them for whatever you want. I mean, they're general purpose, but these are kind of sort of the guidelines as what the compiler will use them for. The segment registers are 2-letter abbreviations, and like I said, they're normally just used for like addressing video memory or file memory, and pointing to the code, data, and stack segments of your layout in memory. The index registers are quite important to know. So EDI is your destination index. So any array operations will be used, EDI will be used as a destination in memory, and ESI the source. So these will often be seen together when you're moving data around. EBP, the base pointer, points to the base of the stack, the current stack frame. So that will move up and down as you're calling through functions. And ESP points to the top of the stack. So the two of them they start off together, and then as the program runs, they'll sort of grow apart. But we're going to go over how the stack looks at runtime later on. And then EIP, which anyone who's done any exploit development will recognize as the instruction pointer, which basically points to the next instruction to be executed. So when you have exploit that smashed the stack back in the old days before ASLR and stack canaries and NX and whatever, you could easily just overwrite sections of memory that you weren't supposed to, and therefore overwrite the stack, overwrite the stored instruction pointer, and when the function returns, you'll end up in wherever that instruction pointer points, which will probably be in your shellcode. And that's kind of the basics of how these stack exploits work. So these are 32-bit registers, so the E stands for extended. On a 16-bit machine, you basically just drop the E and you have your 16-bit registers. But even on a 32-bit machine, you can access these registers in the 32-bit address space, the 16-bit, which is the CX, or you have the high and low 8-bit registers for each of these as well. So you'll often see data being moved into either one of those, depending on the size of the data being moved around. 64-bit is twice as good as 32-bit, and basically they're just going to be called RBP and RCX instead of E. And then we finally have the flags register, which is one big register which holds 22 flags in total, which store operations. So they're binary flags, they're either 1 or 0. And the ones you're probably going to care about most are the 0 flag and the sign flag. And the 0 flag gets set to 1 if the previous operation results in a 0 result. And the sign flag will get set to 1 if the previous operation results in a negative value. Conditional jumps, basically, is what this kind of leads to. So, moving on, calling conventions. So calling conventions are basically how the compiler or how the assembly code calls the next function or steps through the functions. This one's called, well, I call it CDECL, CDECL, whatever. But the key for this one is the arguments are passed on the stack right to left. So if you have a function call with 3 arguments, they'll get pushed on the stack from the right side to the left. So the leftmost one is at the top. And then the return values will get passed back to the caller in EAX. And it's the responsibility of the calling function to clean up the stack when the function returns. This allows for variadic functions, which means variable number of arguments, because the person calling the function knows how many arguments are being passed and is therefore able to clean up that number of arguments. Conversely, standard call, or the Win API call, as it's also known, the arguments and the return values are the same, but in this case, it's the called function, the callee, that cleans up the stack. Hence, no variadic functions. Fast call. So in this case, the first 2 or 3 32-bit or smaller values are passed directly in registers. And it's fast call because these are a lot quicker to access than stack. The rest are then going to go onto the stack. And here the calling function usually cleans the stack. And then finally we've got this call, which only really exists on non-static member functions of C++ classes. The first argument in ECX is this pointer. If anyone's ever done any C++ programming, you always get passed a reference to the current object you're operating on. And again, the called function cleans the stack, so no variadics.
Is there a fast call variant of this?
That one?
Yeah, but for C++.
No, that's the only C++ this call is like a C++ flavor. So then we're going to go over some of the basic operand or operands. So,
It's a mess. Lots of calling conventions.
Yeah. For every operation, there'll be operands, and there's 3 types. There's immediates, which are just standard numbers, you know, any sort of OX3F. There's registers, which is the register value itself. And there's memory addresses. So this is actually the memory reference. So if you look in this point in your memory, the value at that address will get operated on. And the same with the value at EAX will resolve to an address, which will then be the operand. And there's also offset types. So we can do the same with the memory and then basically offset by 4 bytes. And SIB addressing, which is again an offset, but we do multiplication and addition. So you can, you know, use the register values to create this kind of offset into the memory structure at that address. So the 7 ops. There's the move command, the add and subtract. So there's actually more than 7, but I mean add and subtract, we'll count them as 1. Compare, test, conditional jumps and regular jump, push and pop, bitwise ops. So and XOR or not, which basically bitwise operators operate on individual bits of the data. So the move command can take any one of these forms. So you'll operate, this is your destination operand, and this is your source. So you're going to move the data or the value of ECX into EAX. In AT&T syntax, this is the other way around, but there's % signs in front of it, and it gets all a bit noisy. So I just find this a bit cleaner, even though it is a weird way around. In this case, you'll register to register, memory to register, immediate to memory, immediate to register, memory to register, and register to memory. So and then obviously you can do immediate to memory as well. Oh, I've got that there. Okay.
There is no separate store and load instructions?
Not in this case, no, because you can write to anything. Are you thinking of ARM? Yeah. Yeah, no, this is basically allows you to write to memory or registers. Add function is pretty much straightforward. You add 1 to EAX, or you add the value of EAX to EDX. It's add and subtract or equivalent. One just, you know, adds and the other one subtracts. Compare is a bit different. Basically, compare will subtract hang on, let me just get this right. We'll subtract the source from the destination. So we'll subtract that from that, but not store the result. It just throws the result away, but we'll set the flag. Well, it actually sets several flags, but the sign and the 0 flag will be set. So if the 0 flag is 1, we know that ECX and EAX are equivalent. So it's basically, that's kind of how the compare works. It just basically says, you can see which one is larger, and you can see if they're the same. Test is quite similar, except this does a bitwise AND of these two values. So, and again, we'll set the 0 and sign flags depending on the result of the bitwise AND. The result, again, discarded, you don't need it. And then after you do a compare or a test, you'll often find these conditional jumps, and there's quite a lot. So conditional jumps will basically, there'll be an address here or a register memory value, and it will jump to that, considering if it's 0. So if the 0 flag is 1, we'll take the jump. J and Z, if the 0 flag is 0, we'll take that jump. Jump above equal, jump below equal, and I think this was auto-corrected to something else. I can't remember now. Or jump below and not equal, I don't know. But yeah, and there's lots, there's quite a large variety of conditional jumps, but they all start with J, and you can kind of extrapolate what the individual letters mean. Push and pop. These only have one operand, and basically they will put data onto the stack, push. So whatever value is in EAX will get pushed onto the stack. And then if you pop ECX, you'll get the value from the stack popped into ECX. And you can push immediates and registers or values in memory. Bitwise ops, again, you're doing a bitwise AND of ECX into EDX, and the result gets stored in EDX. Bitwise ANDs of immediates, and then obviously the NOT is just a single operation, or a single operand. Right, recognizing some common code constructs. Function prologue and epilogue. This is 3 lines of code that you'll find at the beginning and the end of every function call. And after a while, you'll just read over it because it doesn't really matter. But they're kind of important to understand because they explain how assembly works on a computer. So we enter the function and we push our base pointer onto the stack. So wherever the current base pointer was, and you're now in a new function, the base pointer comes up and it gets stored on the stack. Then we move the stack pointer into the base pointer, creating our new stack frame. And then we subtract whatever value from ESP, which you remember, because it goes up to lower memory addresses, will actually allocate some space on the stack for the local variables that follow. And then when we're done, we move the base pointer to the stack pointer, bringing the stack pointer back down to where the base pointer is. We pop the base pointer off the stack, the one we stored earlier, and then we return. But the thing is, call and return have implicit ops. They don't just call something and then come back. Call will also push the instruction pointer onto the stack just before EBP. So, which is why you can overwrite the instruction pointer with the stack overflow, because it sits below the base pointer. And then obviously return will also pop it, but they're implied by the operations. You don't actually see the push and pops. Okay, so a loop. Given a loop like this, a simple for loop, where we loop an iteration of 20, incrementing x each time, and then we return out. So as I said, ECX is usually a loop counter. They're easier to spot in call graphs than they are in disassembly, obviously. Call graph, I'll show you a call graph in case for those who haven't seen one, but they are kind of weird because compilers do weird things. So I'm going to show you one on an unoptimized compile, which is not what you might see on a different compiler or a different optimization. I mean, if you compile this with GCC 03, you'd probably just see a return 0 because it will just get rid of this because it doesn't do anything. So what you give the compiler and what it spits out might not be as what you expect. So this is our disassembled code. And you can see here, this is the beginning of the loop, where we compare this. So all these EBP minus are local variables. This is an offset of C from the base pointer, offset of 8 from the base pointer. So that's our X and our I. So this is our I compared to 0. So that's our terminating condition for the loop. Jump less or equal to 1FA3, which is here. And if it's less or equal to 0, we come here, we zero out EAX, we clear up the stack, we pop the base pointer and return. So that's our loop exit condition. But let's assume that we're okay. So now we're going to go and move these two local variables. Sorry, we're going to move this local variable into EAX. Then we're going to add X into, or to that value. Then we're going to move EAX into the local value. So that will be our X, that will be our I. And then we're going to move our I back into EAX, and we're going to add -1 because we're decrementing the loop. Again, you could easily have used a sub here, but the compiler chose not to. And then we're going to move EAX back into our local variable and then jump from here back to here to the compare.
It's not really adding -1, it's using overflow, right?
Yes, I guess. But I mean, the other thing is all this moving data back in and out of registers is completely unnecessary as well. So this is, like I said, unoptimized assembly. It's just what the compiler gives you. So that's what it looks like in a call graph. There's an output from Radara, which is a reverse engineering toolkit or framework. There's our entry. There's our loop condition. And if we're 0, we exit down here. Otherwise, we come in here, and then this loop here shows us that this is actually a conditional loop. So using call graphs like this, I mean, IDA has them, but I can't afford IDA, so I use that. Okay, switch statements. Again, there will be quite a few different ways of generating assembly code for switch statements. One of the ones I found early on was quite interesting. It's called a lookup table. So they had this instruction. So EAX was a part of a value that you entered. It's multiplied by 4. So I think it was an int that you entered, a number. And then they had this memory address. I was like, what is it doing there? But then let's have a look at this memory address, and we see this. And then we'll notice that these values, each of these words here, is an endian formatted memory address. And what it does is, given the input value of what you gave it, multiply it by 4, the size of an offset, and add it to here. So if you entered 0, you'd be here. If you entered 1, you'd be here. 2, and then they would use this value to jump to the right case statement in your switch statement, which I thought was quite elegant and nice. And then I thought, I'll see if I can reproduce this. So I did something similar by having an input where A, B, and C, and then a default case statement, default statement. And I compiled that. And this is what came out. It hasn't got a lookup table like that at all. All it does basically is subtract the ASCII value, A or B, from your input. And then if it's equal, so if the operation was 0, it will jump to FOB, which is here. And that will then print this string here, selected A. And if it doesn't, it jumps to here. We'll do subtract 62, which is the B. If that works, then it jumps to here, which will print selected B, and so on, except for that this one will actually jump to down here, which will print the default statement. So again, you don't really know what you're going to get, but it's just quite nice to sort of see this is kind of what these switch statements look like in assembly code. And you'll see that, you know, we haven't really seen anything other than sub, move. Okay, load effective address is one I haven't gone over, but apart from that, there's not really much variety of operands or commands. So the stack. So let's have a look exactly what happens in a stack when we run this. So this is what I've compiled. 2 integers, calling the function add to add them together into another variable, returning that variable into the result, and then we exit out, and that's what I use to compile. So 32-bit architecture, no optimization, Intel assembly, -S basically tells the compiler to stop at the assembly point rather than carry on and do some compiling. And that's what comes out. So here's our add function, that's our main, and there's our call to sim add. So let's see what happens as we see the stack in action. Okay, so we start off, push our base pointer, we move our stack pointer to the base pointer, they both point to the same place in the memory. So the stack's growing up that way. And then we subtract OX18 from the stack, which gives us some slots to put stuff in. And this is calculated at compile time for the fact that you're allocating 3 or 4 integers. And then you'll see here that from the EBP pointer, we're going negative, well, we're subtracting these values and we're going to move these immediates into there. So that's kind of what the stack's going to look like at that point. Then we're going to move those values into EAX and ECX. So these are the numbers we're adding together. Then we're going to move EAX onto the stack at the top, and we're going to move ECX just below it, +4. This is kind of, if you haven't guessed, this is kind of essentially a push op, but compiled as a move op. So essentially you could have pushed ECX and then EAX, and you would have ended up with the same. And then we call sim add, or symbol add, which is our function, which pushes EIP onto the stack. Then we push the base pointer, and then we move our stack pointer and base pointer to the same place. So we're going to shift that all down so we can start with a bit more room. We subtract 8 from the stack pointer, giving us a bit more space. Then we move the, what was it? Oh yes, so the values we pushed here are now going to be used, so they come from here and they're going to be put into EAX and ECX. So that's basically the arguments you're passing into the function. Then they're going to be moved into the local variables, which are assigned here. And then we're going to move one of the local variables into EAX, which goes over there. Then we're going to basically add the local variable back into EAX, which basically performs the addition operation and puts the result into EAX, which is our return register usually. Then we add 8 to the stack, which basically cleans up the local stack, like I said, but this is cdecl, so this function is responsible for cleaning up the stack. We pop EBP and we return, which also pops EIP, giving us the exact address of where we're going to go back to. So now execution resumes at the end. We zero out, so an XOR of any value with itself is 0, so we zero out ECX. We move the return value into our local variable, which is R. Put 0 into EAX because our main function returns 0. We clean the stack by adding the 18 we subtracted at the start, pop the base pointer and return, and we're done. And that kind of is what I was going to go over as a sort of beginner thing. I hope it wasn't too non-beginner. And then there's a plan to have another one where I'll probably go over looking at like a real world example, like a beginner kind of style. Any questions? Anything you would like me to go over? Anything that's really confused you?
So the jump table, were you able to reproduce it?
With my own code? Not yet.
So what if you have like an array of function pointers and then like forced it to like subtract?
You could probably do it that way.
It would probably call it, like literally put a call instruction there or something.
Yeah. I mean, like, if you spend a little bit of time just seeing what assembler comes out of a compile, it's ridiculous. As you up your flags and like your code just gets smaller and smaller, and like you realize that the compiler's a lot cleverer than you are. Sometimes. But yeah, no, I wanted to kind of recreate it with a switch statement and see if I can do it. But so far, I've not really sort of found the magic incantation to sort of get that going. So
What was it that used that local technology?
it was the binary bomb challenge. So there's can't remember the university that did it, but I think UCM, University College Michigan or something. And there's a binary bomb, which is a little 32-bit, there's actually a 64-bit version now, lab thing, which is got 7 stages, and each stage requires an input, and it just stands there and goes, diffuse me. And you have to basically enter the thing, and if you get it right, you go to the next stage, and if you don't, it blows up. And it's a reverse engineering exercise, so you look at the disassembly. I've got the full write-up on my webpage if you want to read it. And you go through each stage looking at exactly what it's doing and why it's doing it, and what the input it needs is. So it's quite interesting, actually. So yeah, I mean, you can read that. I've also got a couple of keygen things on there for reverse engineering things. So then, yeah, next time I was going to go over basically doing a basic keygen from a binary with Radara, which is who's familiar with Radara? No one? Yeah? A little bit, yeah. So basically it's an open source reverse engineering framework, which is an assembler, disassembler, debugger for multiple platforms, multiple architectures. I mean, the guy who wrote it has it running on his, what's the little watch called? Not the iPhone watch, the Pebble. He had it running on his Pebble. It runs on Android, runs on iPhone. He's actually got, there's a Dirty Cow plugin for it now. So all you need to do is just load up R2 and you can exploit Android with Dirty Cow. And so
is that a total IDA Pro sort of alternative?
yes, yeah. There's no GUI for it. I mean, the GUI is pretty much that. No, that doesn't work at all. It's pretty much that. That's your disassembly view, your visual disassembly view. So you can step through this. There's actually, hang on a sec. If I can, nope. Let's mirror displays. That might help. Yes. What's the magic key to? That is it. Okay. So let's have a look. I can't remember what I have on here. Crack knees. So this is one I did recently. So basically it brings you into there, you do, this is not the right way to do it, but this brings you into now. Then you can analyze your imports, your strings, if there are any, which I don't, well, there should be some. Oh no, hang on, this won't bloody work because it's, sorry, there's not a good demo really for it. Let's try again. I blame the laptop personally. Look, I can beach ball. Right. Oh, this is, oh Jesus. Yeah. You were right about this whole don't do it live. Let's just do the AC. Okay. No, that should. Oh, have I? Is this a folder? Is that what I'm doing wrong? It is, isn't it? Yes. Okay. Well, without the highlighting, it's really hard. Okay. So yes, we can look at the entry point. We can look at the information of the binary. It's a bit over to the side.
Use the object dump also for entering the
Of course you can, but this is all in one place. So then, yeah.
You can reverse your Linux binary on your Mac.
Yes, I mean, as long as you're not debugging it, you can look at any architecture on here. So
So the debugger won't work for it.
no. So this is your visual view. On the left-hand side, you'll see. So actually, score dot UTF-8 equals. Well, UTF-8. It actually has UTF-8 arrows, which look a lot nicer than that. So here you'll see. This is the kind of view you'll see from Radara, which your jump arrows, your memory addresses, the opcode or the machine code, the ops, and then any sort of comments and strings that you have in there. And then if you hit V again,
That's a very nice way of learning the assembly, because you see the immediates directly highlighted in the machine code as well.
and this is the function graph view. You can also you can use the mouse on this as well if you wanted to.
What's the right way to write let's say, a non-reversible sort of key acceptor, like the opposite of a key gen?
A non-reversible.
Like
Oh, like so basically this.
if you're trying to write a key gen for something,
Yeah.
it's like the thing that's impossible to write a key gen for. What's the right way to share word key? Just off the top of your head.
Well, I think most of it will be about sort of obfuscation and possibly even sort of runtime encryption of parts of the code. There's also dongles are quite hard. I mean, dongles are still in use. Also, it's not just about the code, but also about the architecture of your key and the software and how it fits together. I guess the more weird you make it, and I guess there's also other ways where people can have remote kill switches if they detect like duplicate keys and stuff like that. I mean, it was a lot easier back then because there was no online. I say back then, when I was at uni, I used to use soft ice and do stuff, but there was no online, so you couldn't have a key revoked because someone else used it because no one knew. So yeah, I mean, it's hard. I mean, I do this as a hobby. It's not what I do for a living, so I'm sort of not a professional. So I'm still sort of learning a lot as I go through and whatnot.
I think Skype used the method, the old Skype, not the new one, where they always, I call it code obfuscating. They had pieces of code always obfuscated, and before they called this piece of code, they had to decrypt, obfuscate it and called it. So it was not really, the problem was when you saw it in some of these tools, you couldn't just see it, because not all at once, because
This one has a debugger as well, so you can see it.
Yeah, you could follow it, but you would always go through the steps where it had to de-obfuscate the pieces of code, and the other ones were obfuscated again, so it was a bit ugly.
Yeah, so immediate view would be difficult, but when you figure out how to de-obfuscate it, then you're winning it. But that's the hard part.
Yeah, but still, it was quite successful.
Yeah.
Then it was the old Skype. I mean, the new Skype, they changed everything.
Yeah.
So and they.
I mean, there was a copy protection, Spyro the Magic Dragon on the PlayStation, and that was, I think it still is. It took the longest time to actually crack properly of any sort of scene back then, and the way they did it, that's because normally there's for the copy protection on discs, you'll change. I mean, you can actually get around this by so somewhere there, well, further down there'll be. Somewhere, I should do a search, too lazy. Somewhere, well, basically somewhere there's a like, yes, you've basically got it. And at some point there'll be also a conditional jump to, no, you didn't. You can patch that jump and you've basically achieved the same thing, but it's more challenging to get the key gen. So what they do with the copy protection is they often have checksums running on the code in the game. So when you get a copied disk, they'll also do a checksum to make sure everything's okay and then work or not work. But what Spyro the Magic Dragon developers did was they didn't have a checksum function. They did everything in line. So you couldn't just patch the checksum function. You had to find this function everywhere in the code. And then it didn't just break the game, it just made one of the crystals not appear in a level that you needed to get to the next level. So you had to copy the game, patch all the things, and then play the whole thing before you knew that you did it. And that was genius. And it took, I think, 4 months for an actual working release to come out. So, yeah.
But it's also price for developing this kind of stuff.
Yeah.
I mean,
Yeah.
it's the way. I mean, if you have quite funds, I mean, then you can do development.
Funds and time, yeah.
Yeah. Yeah, fun. Yeah, I mean, but basically, I think it's the money is the main thing.
Yeah.
I mean, if you know you have a big sell afterwards, then you can do that. But otherwise,
Yeah.
it's not worth it.
But I mean, it also got quite a lot of interest because a lot of groups were just out there trying to
Yeah,
make this crack, and they couldn't. And so,
Okay.
but yeah, I mean, this is just like a overview of the tool. There's some other command line tools, like RASM, which basically allows you to do. Oh yes, which basically allows you to compile instructions into machine code, and vice versa. In the 89C8. So you can use that, and there's RAG2, which basically allows you to compile shellcodes and disassemble shellcodes. RARBIN, RARDIFF, which is a binary differ. I mean, it's huge. It started off as a project to recover, a hex editor actually, to recover data from a hard drive. And 10 years later, we've got this IDA competitor open source tool. So I think so, yeah. It probably was this.
It's like the greatest yak shaving ever.
Yeah. So yeah, no, he wrote this tool because he couldn't find anything to do it, and it kind of just grew. So this is Radara 2. So yeah.
What other architectures does it do?
Those. I've got to make it so small you can't even see it.
Super LED CPU.
Scalextrics. Did you say Scalextrics? Yeah. That's a language. It's just made up of dashes and brackets, I think. And I said it runs on, it's written in C, so it runs on pretty much any platform. There's also Radara 2 extras, which allow you to have more plugins, because the whole project is actually LGPL licensed. So any GPL plugins are in a separate repository, and you have to actually install them with their package manager. Because the Debian people cried about it, they said we can't have these by default. So. And I've been working on the x86 handmade assembler, the Z80 assembler, and porting stuff over to the extras that wasn't LGPL licensed. So I contribute to this in my spare time. So, but yeah, check it out. Always get the version from Git, github.com/Radara, which is spelt like this. You see at the bottom? No, not really. But yeah, and basically, yeah, just.
Italian?
Sorry?
Is it Italian?
Spanish.
Oh, Spanish. Okay.
The original author
Yeah,
Spanish. Yeah.
Okay.
It actually stands for something. I can't remember what it is now. Something data and recovery. Blah, blah, blah.
Because it sounds romantic or something.
Mm.
And then now with better English.
Oh yeah, they have the fortunes are different every time. So.
Oh, right.
Yeah, I love the smell of bugs in the morning and whatnot. So, yeah. Oh yeah, and it's customizable. You can change. It has color themes and whatnot. So that's what I'm going to be. I'll go over next time is actually using it to look at that simple keygen, and then write the keygen.
It's fairly complete, isn't it?
Yep. Got a lot of contributors. And it also has this thing called SIL, which is a VM, so you can load up a binary into R2, and then you can configure your registers and stack exactly how you want it, and then step through the instructions as if it were running.
Oh, it's just an emulator. Oh, that's
Yeah.
right. Yeah, that's good.
But one that you control the entire architecture
Yeah.
beforehand.
Oh, you could use it for education.
Yeah.
Excellent.
Excellent.
All right, thanks.
That's been really good, yeah.
Cool. Glad you enjoyed it.